Okay, so now we want to apply refraction to the use of lenses. So just like we had two kinds of mirrors, we have two kinds of lenses. So we have a convex lens, where the middle of the lens pushes out, and the concave lens, where the middle of the lens pushes in at the middle. Notice this can be a bit more complicated than the case of the mirrors, because mirrors just have one surface, whereas with a lens there are two surfaces to the lens. So that means that, say, one side can be convex and the other side can be concave. So in general, we're going to mostly think of it as a converging lens or a diverging lens. So a converging lens means that the refracted light meets and forms a, well, if it's all parallel, it'll have a focal point on the opposite side of the lens. And if it diverged, then after it goes through the lens, then the light rays will never meet, and so then it will appear to come from a virtual image on the same side of the lens that the light came from. So in general, we're mostly going to refer to these as diverging and converging lenses. Although in general, if you have a double convex, that's going to be a converging lens, and if you have double concave, then that's going to be a diverging lens. So when we solved the image location in mirrors, we used the mirror equation, which told us that one of the objects, or 1 over the distance to the object plus 1 over the distance to the image, is equal to 1 over the focal point. The main trick was remembering the signs, so when is the sign positive or negative, but since there's really only one side to a mirror, if you're looking at the reflecting side, your position is positive, and if you're looking at the opposite side of the mirror, that position is negative. For lenses, we consider the object to be positive when the object is real and is the source of light before hitting the lens, while for images, the image distance is positive on the opposite side of the lens. So if the image is real and the distance is positive, and if the image distance is negative, then the image is imaginary. So notice this is different from the case of the mirror. So if it's on the opposite, if the image forms on the opposite side of the lens, then the image distance is positive. Also, the convention is that the focal length is positive for converging lenses. So if the convergence point, the focal point, is on the opposite side of the lens, the focal point is positive, and it's negative for a diverging lens where the focal point is on the same side of the lens as where the object is. The magnification is positive if the image is upright, and it is negative if the image is upside down. Okay, so notice that the problems here are really pretty similar to what we did with mirrors, only the sign conventions have changed. We also need to go through the different regions, with region 1 having the object beyond the center point, where the center point is twice the distance as the focal point, region 2, where the object is in between the focal point and the center point, and region 3, where the object is inside of the focal point. Okay, so next I'm just going to walk through these different options for a converging lens. Okay, so now we want to look at some examples where we have some converging lenses. So in the first case, we're going to take the example where the lens has an object that is infinitely far from the lens. So that means that the light rays coming from the object are all running parallel to each other like so. So that means when they hit the lens, they're going to converge, and they're going to converge at the focal point. So remember, in this case, our object over here, so it is where the light's coming from, so it's positive infinity. And then the focal length, so this is on the other side of the lens. So for lenses, this side is positive for images and for the focal lengths. So if we have a converging lens like this one, that means the focal length is positive. Okay, so if we do this, we see that the parallel light rays should focus at the focal point, so that would kind of suggest the image should also form at the focal point. But let's use the lens equation to see if this is correct. So our lens equation, 1 over the distance to the object plus 1 over the distance to the image is equal to 1 over the focal length. So the distance of the object is infinity, so 1 over infinity is just 0. This becomes 1 over distance to the image, and this becomes 1 over f, which is 10 centimeters. So since this is 0, this becomes 1 over di is 1 over 10, and di is equal to 10 centimeters. So the image also forms here, and so that's telling us that the image will form at the focal point, which is kind of what we expected from the ray diagram. If we do the magnification, this is the negative of the distance to the image divided by the distance to the object. So the distance of the image, so this is negative from the formula times 10 centimeters, and the distance to the object is infinity. So this means the magnification here is 0 because, well, it all focuses at the focal point. So essentially the height of that image is going to be 0. So the magnification is 0. Okay. So let's try our next case where we have an object that is in region 1. So region 1 here is beyond 2 times the focal length. And so in this case, we've drawn a couple of the rays here. So this is the P ray, so it runs parallel to the lens, then it focuses through the focal point, and then crosses where it looks like the image is. Next we draw our C ray. So our C ray goes through the center of the mirror. So this tracks here right at the center, keeps going straight, and so it meets with the P ray on the opposite side of the focal length. If we wanted to write the last ray here, so this would be the F ray, so this would go through the focal point. So let's see here. I'm very bad at straight lines, so it would go through the focal length, and then that means it would run parallel once it hit the lens here. So I missed by a touch, but the point is the image should form past the focal point, and it does kind of look like that image is smaller than our original object. So we're kind of expecting, and it's definitely inverted, so we're expecting a magnification that is negative and the magnitude is less than 1. So to solve for this more precisely, we use our lens equation. So 1 over di plus 1 over do is equal to 1 over f. So the object is 26 centimeters, 1 over di divided by the focal length, which is 10. So probably this one requires a calculator, so this becomes 1 over 10 minus 1 over 26 is equal to 1 over di. So you would do this answer and then divide 1 by this answer. That gives you that the distance to the image is 16.25 centimeters. So that means the image forms at 16.25 centimeters, so that is a little bit past the focal length, which is 10 centimeters. It's on the opposite side, which is positive for lenses, so this all seems to check out. If we want to find the magnification, it is negative di over do, so that is negative 16.25 divided by 26 centimeters, so the magnification is negative 0.62. So that also checks out, right? The magnification is negative because the image is inverted, but also its magnitude looks like it's less than 1. So yeah, negative 0.62 looks about right. Okay, let's move our object in. So I'm going to skip the double focal length. So now we're in region 2 where we are in between the focal length and 2 times the focal length. So in this case, we've got our image. Looks like it's on the opposite side and it's inverted. If we draw our third ray, our F ray, this will also go through the focal length, and then it will run parallel once it hits the mirror. And so that means it looks like our image is now larger than our object. It's also inverted, so we expect the magnification to be negative and larger than 1. So to confirm this, we use our lens formula. So 1 over do plus 1 over di is equal to 1 over f. So distance to the object is 18. Distance to the image is what we're trying to find, and this is 1 over 10 because 10 is the focal length. So this one also you're probably going to need a calculator for 1 over 10 minus 1 over 18. So then you will do 1 divided by 1 divided by 10 minus 1 divided by 18. And if you do that, what do we get? We get a distance of 22.5 centimeters. And so that seems reasonable. We are past the focal point, so 10 is the focal length, and it's well past that. And our magnification is negative di over do, so that is negative 22.5 divided by 18, which is equal to negative 1.25. So this also checks out. Our image is inverted, so the magnification should be negative, and it's a bit larger than the original object, so the magnitude is greater than 1. So all checks out. So notice, as we've been moving through, we started out at infinite distance, the magnification was 0, and we were in region 1, the magnification was between 0 and negative 1, and now that we're in region 2, the magnification now becomes greater than negative 1, or less than negative 1, the magnitude is greater. And so then now what happens when we move through to the focal length? So at the focal length, we have an interesting situation because, well, I guess if we tried to draw our third ray here, we're in a bit of a mess because the F ray is going to be pointing straight down. So it's not really going to hit the mirror here, but eventually it will. I mean the lens. But in any case, what happens is it sure looks like these two rays don't intersect. So what does that mean? So let's look at the lens equation to figure out what's going on. So it's 1 over do plus 1 over di is equal to 1 over the focal length. So the distance of the object is 1 over 10. 1 over di plus 1 over 10, and so that means this becomes 1 over di of 1 over 10 minus 1 over 10, which is equal to 0. So if 1 over di is equal to 0, then that means di is infinity. So that means that the image never forms, so it travels off to infinity, and these rays never intersect with each other, so no image is ever formed. So that means if we're trying to find the magnification, this is negative di over do. So let's see, negative di, so that is negative infinity over 10. So that is negative infinity. So I don't know, it's kind of undefined here since the image never really forms. You could think of it as the, magnification here, though, is infinite because it's, the image would be infinitely large since it keeps going on and on. All right, so last one. So now we move through the focal length, and now we're within region 3. So what happens now? So now if we try to draw our rays, we notice that they do not converge, right? So that means something must be going on. So that means the rays converge on the same side as the lens as the original object. So that means that it's a virtual image rather than a real image, and so the image position should be negative here. So if we do this, 1 over do plus 1 over di is equal to 1 over the focal length. So 1 over 5 plus 1 over di is equal to 1 over 10, or 1 over di is 1 over 10 minus 1 over 5, or 1 over di is equal to, negative 1 over 10. So that means di is equal to negative 10 centimeters. So it should form roughly, actually at the center point here. So that means that because the image is negative, that means that it's going to form on the same side of the lens as the object. So it's going to form to the left. And it also means that the image is virtual. So there's no spot where the rays actually cross. It just looks like they do cross. Okay, and then if we want to do the magnification, so this is negative di over do, so this is equal to negative, and the distance to the image is negative 10, and divided by the distance to the object is 5, so that means that the magnification here is 2. So that means that once our object is inside of the region 3 inside of the focal length, then that means that the image is going to be larger than the object itself. The image is going to be upright, so it's going to be a virtual image. Okay, so yeah, so the idea here is to track through the different spots. So when you start out at infinite distance, your magnification is 0. As you move closer to the focal length, so the magnification is negative, so the images are inverted, but that magnification gets larger in magnitude until you hit the focal length. Then the rays never converge, so there isn't really an image formed at that point. And then once you go through the focal length, then again the magnification now is positive and very large, and so, or greater than 1 at least, and so that means that you now are forming a virtual image, and it's formed on the same side of the lens as the object itself. Alright, so that's it for our converging lenses. I guess we'll take a quick look at diverging lenses in the next vid.